So in this video we are going to discuss a truly incredible theorem in calculus, which is Taylor's theorem. We're going to start by stating what this theorem says, and then we'll spend most of the video explaining why it's true, doing a calculus proof of this. And don't worry, I'm not going to pull the wool over your eyes. We are going to see the reason that this incredible theorem holds true. By a calculus proof, I mean that we will take as premise Rolle's theorem, and don't worry, if you don't remember what Rolle's theorem is, I will remind you. It's a perfectly intuitive theorem, but we're going to take that as our starting point. We're not going to prove that. Proving that is an analysis job rather than a calculus job. So we will understand, given the premise of Rolle's theorem, how it implies that Taylor's theorem is true. Then, finally, we'll end the video by looking at an example of applying Taylor's theorem. So we will look at the Taylor expansion of e to the x, and we will use Taylor's theorem to prove that that Taylor polynomial does converge to e to the x everywhere along the real line. Now, as I've already said, this video is going to be a calculus video rather than an analysis video. So we are going to see the incredible parts of the proof, but we're not going to get bogged down with full-level analytic rigour. In particular, if we were studying this theorem from an analysis point of view, we would specify exactly how many times the function needs to be differentiable in order for you to apply Taylor's theorem. We're not going to worry about that here. We're going to view it from the calculus perspective. In calculus, all the functions that we deal with are generally continuous at most points. Usually the only times that they'll be discontinuous are if they've got an asymptote, and usually they'll have a finite number of those, so they'll be discontinuous at a finite number of points and continuous everywhere else. And then they're also infinitely differentiable, again, at nearly all the points apart from finitely many. So we're going to assume that those are the types of functions we're dealing with, continuous and infinitely differentiable. We're not going to try and reduce the criteria to as minimum as possible as you would do in analysis. We're not going to say it's actually only necessary for the function to be this many times differentiable in order for you to apply this theorem. We're just going to assume that the functions we're dealing with are the calculus functions, the ones that are infinitely differentiable, just so that we don't have to get worried with those sort of technicalities that you would worry about in an analysis course. We're going to see the really interesting parts of this theorem rather than worry about the more complicated but more boring technicalities. So, with that said, let's begin. So we're going to take one of these calculus functions then, f of x, which we will assume is therefore continuous and infinitely differentiable, and we're going to perform a Taylor expansion of it. So we'll use some notation throughout this video, which is we will call the Taylor polynomials p, and then we'll have n of x. And this means the nth Taylor polynomial for my function. So this means f evaluated at some a, and by the way, we'll assume we're centering the Taylor expansion around some x is equal to a, so just drawing a picture here. So here's 0, and maybe here is a. So we're centering the Taylor expansion around a. So it will be f of a, and of course if we're looking at the zeroth Taylor polynomial, that will be it. So p0 of x would just be f of a. Then the first Taylor polynomial would be f prime evaluated at a times x minus a, plus then if we go up to the second Taylor polynomial, we'll have to add on the second term. So the second derivative times x minus a squared over 2 factorial, which is just 2, and then it goes on all the way up to the nth term of the Taylor expansion, so fn evaluated at a, x minus a over to the power of n over n factorial. So that's the Taylor polynomial, the nth Taylor polynomial. And what Taylor's theorem is all about is saying we want to fix this. This is not, for the general nth Taylor polynomial, this is not going to equal this for a general function, unless it happened that this function was actually just that polynomial. But if we imagine this function is e to the x, then the nth Taylor polynomial is not going to be equal to that. the question we are going to ask is, if we consider some specific x value, some x0, can we add another term onto the nth Taylor polynomial that fixes it? And let me show you what I mean by this. So if we have f of x and we're approximating it by this nth Taylor polynomial, and at the moment the only place where we know it's correct is at a, because if you put in x is equal to a, all of these go to 0 and you just get f of a, so it's correct there. But what I want to say is I want to make it also correct at this point x0, and the way I want to do that is by adding the seemingly next term onto the Taylor polynomial. So I want to add something of the form x minus a to the power of n plus 1 over n plus 1 factorial. And now I want you to pick that coefficient really carefully so that it's correct at x0, so that this thing, this approximation, will not just be correct at x is equal to a, and I'm pointing at the wrong point. The 0 and the a look too similar to one another. This is a. I might just colour in a. So this circle with a red circle is a. So we know it's going to be correct at x is equal to a, but we now also want our approximation to be correct at x0, and I want to know what coefficient would I have to put in front of this term to make this new polynomial correct, not just at there, but also at there. And you can work that out. All you'd have to do is put in x0 to everything. So we'd say f of x0, we want this to equal the Taylor polynomial evaluated at x0 plus c times, and then we've put in x0 for x here as well, all divided by n plus 1 factorial. So if I want to know what coefficient, what c I'd have to put there in order to make this work, all I now have to do is rearrange this equation. This is now not a function anymore, this is just an equation because we've put in a specific value, a specific real number x0. So this is a number, this is a number, this is all a number as well. So we can just rearrange this. So we would get that c is equal to, we'd get n plus 1 factorial, which is a number, divided by x0 minus a to the n plus 1, which again is a number, x0 is a number, a is a number, n plus 1 is a number, and then it's multiplied by f x0 minus pn x0. And again, those are just numbers. They're those things that were functions now evaluated specifically at x0. So my point is that you could find a coefficient, it would be this, that you can put there that would make this new thing, this higher degree polynomial of degree n plus 1, it would now be correct at a, and it would be correct at x0. It might not be correct anywhere else. All the points in between a and x0 might be completely wrong, and then beyond also might be wrong. But at least it will be right at a and it will be right at x0. This is then what Taylor's theorem says. It says that there exists some point that is between a and x0, some point in that little interval there. I'm going to give this a really fancy Greek symbol just to be annoying, so we'll use the Greek symbol xi, which is beautiful. There exists some point xi in between a and x0 such that c is equal to the n plus 1th derivative of the function f, the original function, evaluated at xi. So it says this magic number that you need in order to make this thing right at x0, this is actually equal to the n plus 1th derivative of your original function evaluated for some value in between a and x0. So that would mean that this new approximation, so f of x, is approximately equal to our Taylor polynomial, our nth Taylor polynomial, plus this fn plus 1 evaluated at xi, and I'm going to regret using that symbol, having to draw this out so many times, x minus a to the n plus 1 over n plus 1 factorial. And now this thing will be right at x is equal to a and at x0 for this given xi. And no matter what x0 you pick, you can pick whichever one you like, there will always exist a xi in between a and x0. So if x0 is all the way over here, there'll be some xi that's in that interval, such that when you plug it into the formula for the n plus 1th derivative, it gives the perfect coefficient that you need there in order to make this thing right at x0. And that holds true whether x0 is on the right of a or whether it's on the left over here. So if it was down here, again, that interval between x0 and a would contain a xi, something. It doesn't tell you what that xi is. That's not what Taylor's theorem does. But it tells you that there exists a xi. So that's what the theorem really is. There exists a xi, which is an element of that interval. And if we're imagining that a is on the left and x0 is on the right, so is an element of the open interval, so it's not either one of the boundaries, it's something in between them, such that it's the magic coefficient that makes the polynomial that we've got here suddenly work at the point x0. And you can do that for whatever x0. The xi will change depending on which x0 you're taking, but for every x0 there must exist a xi. So I'll put that here. For all x0 is an element of the real line, there exists a xi. So that's what Taylor's theorem says, and we're going to now understand why that's true. So this theorem is actually really a generalization of the mean value theorem, which is a generalization of Rolle's theorem. And the entire proof that we're going to do relies completely on Rolle's theorem. So I'm just going to remind you what Rolle's theorem says. So this is a perfectly intuitive theorem that we are not going to prove. The reason we're not going to prove it is that it's very intuitive. It's not something that is unintuitive. You know, Taylor's theorem that we've just stated is not an intuitive result. You look at that and think, my goodness, why on earth is that true? It's not obvious that that's true at all. Rolle's theorem is a result that you look at and think, my goodness, that's trivial. Why on earth is that given a name? It's obvious that that's true. But it's kind of like the intermediate value theorem, which again is something that's really obvious it's true. And in calculus, you just say, yes, that's really obvious that's true. Picture shows exactly why that's true. And that's exactly what we're going to do for Rolle's theorem. We're going to draw a picture. But then when you actually try and prove these things that you think are really obvious, it's actually really much more complicated. And that's what they do in analysis. You prove these things that you think are intuitively true, but actually it turns out to be really complicated. We're not going to do it here. Rolle's theorem proof is truly across that border into analysis rather than in calculus. In calculus, we just look at the picture and say that's obviously true. In calculus, you know, we prove really unintuitive results like this result that we're about to prove, Taylor's theorem. And it's amazing how simple the proofs are, and it really is. This proof is not complicated, what we're going to do, and we're going to prove an amazing result. Whereas in analysis, you prove results that are really intuitive, really simple, and it's amazing how complicated the proofs are. So we're not going to prove Rolle's theorem, but I will just state what Rolle's theorem says. So picture. So if we have some function, which we'll call f of x, and we have two values on the x-axis, a value a and a value b, and don't get confused with the a that we've used previously. This has nothing to do with what we've done previously. And we're now going to assume that the value of the function at a is equal to the value of the function at b. So I could draw like a dashed line across there. So here is the function evaluated at a, f of a, and here is the function evaluated at b. So f of a is equal to f of b. Then what Rolle's theorem says is that if you have some function that is one continuous all the way between a and b, so it needs to be continuous on this interval from a to b, and it needs to be differentiable everywhere apart from at the two boundaries, because it doesn't necessarily need to be differentiable there. If it's only defined, it doesn't need to be differentiable at the two boundaries. It could have corners there. Differentiable everywhere, apart from necessarily at the boundaries. It could be differentiable at the boundaries, but you don't need differentiability at the boundaries for this to be hold true. So differentiable everywhere on the interval AB, the open interval AB. Then you can conclude that somewhere in between A and B, and I'll use the same magical Greek symbol, there exists a zeta, sorry, not a zeta, a xi, which is an element of this interval AB, and it's not one of the boundaries, so it's an element of the open interval AB, such that the derivative of the function at xi is equal to 0. Now, this is a perfectly obvious theorem when you think about what it means and you look at the picture. So, if we think about what this function could be, one option is that it's a straight line connecting these 2 points. It just stays constant. It remains at this value, f of a, which is f of b. Now, if it's a straight line, then everywhere on that interval between a and b, the derivative is equal to 0. So truly, it's true that there is something in that interval where the derivative is 0, and we could mark xi maybe on here. So everywhere it's true. So it's true, therefore, that there exists a xi where the derivative is equal to 0. Now, if it doesn't stay constant, then it either goes up or it goes down. So if it goes up, at some point, if it's going to come back down to f of b, then it has to turn, because remember the function is continuous, and the intuitive definition of continuous is that you can draw it without taking your pen off the paper. So if it's going to come back down to f of b, it must turn around, and at that point where it turns around, that critical point, that's where the derivative is going to be equal to 0. And the fact that it's differentiable everywhere means that you can't have, for instance, a corner. So another option would be something like what I'll draw in red here. It could do something like that. That would be continuous. But why would that not be allowed? That wouldn't be differentiable everywhere. At that corner point up there, it wouldn't be differentiable. So that's why that's not allowed. So if it's differentiable everywhere, it can't have corners like that. So instead, when it turns around, there must be a point, a critical point, which is where the derivative is equal to 0, rather than the critical point where the derivative doesn't exist. And similarly, if it goes down instead, rather than going up, again, to get back up to f of b, it has to turn around, and it will have to do that at a critical point where the derivative is equal to 0. Again, using the fact that it's differentiable everywhere, so you can't have a corner to turn around. So that's Rolle's theorem, that if the function is equal, if you've got a function over some interval ab, and the value of the function at a is equal to the value of the function at b, the function is continuous on that interval, and it's differentiable everywhere in the middle of the interval, so on the open interval ab, then it's true that somewhere in that interval the derivative must equal 0, i.e. there exists a xi in there such that the derivative is equal to 0. So we're not going to prove that. I hope that it's perfectly intuitive that that is true. There's the pictorial calculus proof in inverted commas. But proving that is an analysis job, and even though it's a phenomenally intuitive result, it is a complicated proof that requires you to look at the definitions of continuity and differentiability in detail, and we're not going to do that in here. Truly, it's crossed the realms into analysis. It's no longer calculus. So we will go back to using this to prove Taylor's theorem, and it's incredible how easy this is now. So to business then, and the way we're going to do this is we're firstly going to start off with some simple examples, the low order cases, and then we'll generalize it to the nth order case. So let me show you what I mean. So we're going to start off with using the zeroth Taylor polynomial, which is f evaluated at a. And we're going to say, let's draw a picture. We have our a here, and we have some x0 here, and we want to add on the next order term along that is going to make this approximation right at x0. So at the moment we're approximating f of x with this zeroth Taylor polynomial, and now what we want to do is add on the next term along. So we want to find this coefficient c such that c times x minus a, this new approximation, this first degree approximation, if you evaluate it at x0, we want it to be correct there. At the moment initially this thing was just right at a. It might have been right elsewhere, but the only place we know that it was right was a. Now what we want to do is make it right at x0, and we know that we can do that. We know, as I've shown you previously, that there is a c that you can put there, so assume that you have put that correct c there, so that this thing truly is right at x0. So what you can now do is you can consider the difference between the two functions. So I'll call this d of x. So we can define d of x to be equal to f of x minus this new approximation, which is the zeroth Taylor polynomial plus this additional correction term, we might call it here. So we've now got some new function. And what can we say about this? Well, because this was right at x is equal to a and x0, we can say that this difference is equal to 0 at those 2 points. So if we were to draw the difference, maybe it might look like something like this, just a random picture there. The important thing is that it's 0 here and 0 here because we chose this c such that this worked and gave the correct answer there. So when you subtract this off from this, it will give 0 at that point, and we know it will give 0 at a. Now, we know that the value of this difference is equal to one another at these 2 points, so we can now apply Rolle's theorem because this is exactly the case that Rolle's theorem applies to. So we can say that somewhere in the middle, the derivative will equal 0, so there'll be some xi here in between a and x0 where the derivative is equal to 0. So now let's differentiate our function. So d prime of x is equal to f prime of x. F of a is a constant, so that disappears, and then if we differentiate c times x minus a, that just becomes minus c. So this is the derivative of that difference, and we know that there exists, for some xi in between a and x0, this is equal to 0. So f prime xi minus c is going to equal 0 for some xi which is in that interval, that open interval between a and x0. And that was done by Rolle's theorem there. And you can see how we're already getting somewhere here. So now what we've shown is that that c will equal some derivative of the function f evaluated at some xi that's in that interval. So that's the first result there. We can put in for c here f prime of xi. So we have that f of x is now being approximated by f of a plus f prime xi x minus a. And this approximation will be correct at both x is equal to a and x is equal to x0. And if you plug in x0 in place of x here, then this will therefore become an equality. So get rid of the approximate, the equal to, and it will actually be equal to. And of course, that is the mean value theorem in disguise there. If you just rearrange that, that's the mean value theorem, that there exists some xi in between a and x0 such that f prime evaluated at that xi is equal to, and then we'll have f at x0 minus f of a all over x0 minus a. So the first degree case, or the 0th degree case of Taylor's theorem is actually the mean value theorem, and that's what I mean when I say that Taylor's theorem is a generalization of the mean value theorem. Let's now do the next degree case up, and then we'll see the general pattern and we'll do it for the nth degree case. So now what we're going to have is we're going to have the first degree Taylor polynomial as our approximation. So it's going to be f of a plus f prime of a times x minus a. So we're approximating our function f of x with this first degree Taylor polynomial. And now what we want to do is add on the next degree term. So we want to add c x minus a squared over 2. And we want to do that in such a way that it makes the function correct at our x0 again. So drawing a picture again. So we've centered our polynomial at a, and we've now got some x0, and we're always taking x0 to be on the right just because it's easier on our brains that way round, but this entire argument works exactly the same way round if x0 is on the left. It's going to be that the xi is in the interval between the two. And in that case, x0 will be the smaller one, so it will be the interval from x0 to a rather than the interval from a to x0. But just because we all prefer this way round, it looks nicer, so that's the reason we're doing this. So as we showed before, there will be some c that exists that makes this perfect at x0. It won't be perfect everywhere else, but there is a c that makes it perfect at x0, and the way that you can work that c out is just by plugging in x0 and rearranging for c, and that's the c that you have to make it. But what we're going to show about that c is that it's actually going to be equal to the second derivative of the function evaluated at some xi that is in between a and x0, and we're going to do that by Rolle's theorem. So now again what we can do is we can consider the difference between these two things. So we'll call it d of x, and it's going to be equal to f of x minus our approximation, so minus the first degree Taylor polynomial and minus this correction term, cx minus a squared over 2. And again, what I know is that because this was right at x is equal to a, and because it was right at x is equal to x0, the difference between them will now be 0 at these 2 points. So again, I can draw some picture that might look like, I don't know, this thing here. So the important thing is that it's going to be 0 here and 0 here. And then again, I can apply Rolle's theorem to say that somewhere in the middle, the derivative will be equal to 0. So we can now differentiate this. So differentiating this function will give f prime of x. And then differentiating the first Taylor polynomial, where is our first Taylor polynomial here? So this bit will go, and then we'll have just the f prime of a left, because when we differentiate this, it just goes to 1. So we'll have minus f prime evaluated at a, and then differentiating this bit will give minus c times x minus a. Now, we're not actually interested in plugging a xi into here and saying that that's going to be equal to 0. That's not what we want to do. We're actually going to apply Rolle's theorem again, and this is how. So this place, and on the picture it's here, this place where the derivative, the first derivative is equal to 0, we will call that alpha. It is not xi. It's not the xi we're looking for. What we can now do is apply Rolle's theorem to this function, which is the first derivative. So if I imagine plotting another function, so this function that we had plotted here was the difference. Now what I'm going to do is imagine plotting d prime. So here's a, and here is x0, and here is that point alpha where we know that the derivative is equal to 0, because we know by Rolle's theorem that such a point will exist. The other thing I want to point out to you, that even though it doesn't look like it on this picture, the derivative at a is also equal to 0, because if you look at this, if you plug in x is equal to a here, this bit goes to 0, and then you've just got f prime at a minus f prime at a. So because of the way the first Taylor polynomial was, it perfectly gave that first derivative. So when you take the difference of the two, they're going to get rid of each other. So actually, d prime is also going to be equal to 0 when x is equal to a. Now, I know this picture doesn't show that. It shows a nice negative slope there. But if it was more accurate, it would have had derivative equal to 0 there. So it should have been flat there. And I've just made a mess of that picture, but hopefully you get the point, and you can probably see where this is going now, because this d prime, it's going to be equal to 0 at x is equal to a, and it's going to be 0 at that x is equal to alpha. And now what we can do is apply Rolle's theorem here again and say that there must be a point in the middle of a and alpha such that the derivative of that function, which is a derivative itself, so the second derivative is equal to 0. And that point is now going to be our xi. So let's do this. So we will differentiate this difference again. So the second derivative will equal the second derivative of f. Now, this is just a constant term, so this has vanished. And then we'll just have minus c. And what we know is that there will exist a point between a and alpha where this is equal to 0. So this will equal 0 at some xi. So f double prime of xi is equal to c, therefore. So that's how you can prove that for, in this case, c is going to equal the second derivative of our original function evaluated at some xi. And xi is going to be somewhere between a and x0. And the reason we say it's between a and x0 rather than a and alpha is that we don't know what alpha is. We don't know where alpha is. Alpha might be right up here, right next to x0. You know, it could be indefinitely close to x0. So in general, all we can say about xi is it's somewhere in between a and x0. So xi is somewhere in that open interval between a and x0. And now this argument extends. In the third case, you just apply Rolle's theorem 3 times. In the fourth case, you apply Rolle's theorem 4 times, etc. So we'll now do the general nth degree case. So the general nth case then. So we'll come down here. So we're now looking at the nth Taylor polynomial. So this will be f evaluated at a plus f prime evaluated at a, x minus a, plus f double prime evaluated at a, x minus a squared over 2 factorial, plus all the way up to f differentiated n times evaluated at a, x minus a to the n over n factorial. And we're using that as an approximation to our function, so f of x is approximately equal to this. And again, the whole idea of this is we're going to add on a correction term, so we're going to pick some x0, so drawing a picture again. So we have our a here, that's the centre of the Taylor polynomial, and then we're picking some x0 here, and the idea is we want to add on a correction term that makes this correct at x0. It's not going to fix it everywhere, but it's going to fix it at least x0. So we're now going to add on this correction term, c times x minus a to the power of n plus 1 over n plus 1 factorial. And again, we know that we can make that c because you just need to plug in x0 into f, plug in x0 into this nth Taylor polynomial, subtract the two from one another, and then pick the c so that this thing works out. So put x0 into here, that just makes a number, and then you just need to divide f of x minus the Taylor polynomial evaluated at x0 by that number, and you'll get what c is equal to. We're not going to do that to find c, however. We're going to actually show this thing about c another way. We're going to show that it's actually equal to the n plus 1th derivative of f evaluated at some xi in between here. So Same argument as before. We're going to construct this difference. So d of x is going to equal f of x minus the nth Taylor polynomial, and then minus our correction term. So c x minus a, so that n plus 1 over n plus 1. And now, because we chose that c so that it was right at x0, what we can say is if we draw d on here, and I'll try and do a better job of drawing d this time. So if we draw d, it might look something like this. And what we can definitely say is that it's going to be 0 at a and 0 at x0. And then we can apply Rolle's theorem the first time, and we're going to apply it a lot of times here. We're going to apply it n times. We can apply Rolle's theorem for the first time to say that there will exist some point in between here, and I've drawn it at the wrong point. On the picture it's here. So there will exist some point alpha there, such that at that point the derivative is equal to 0. So differentiating this, we would get d prime of x is equal to f prime of x minus, then I'll just write the derivative of the nth Taylor polynomial, minus c x minus a to the power of, well, and that should be an n plus 1 factorial, which we've dropped there, to the power of n over n factorial. Now, we're not actually interested in what that alpha is. The key bit that we're interested in is now we can apply Rolle's theorem again, because we've got this point where the derivative is equal to 0, and we know that the derivative of this difference is also going to be 0 at x is equal to a, because looking at this, this Taylor polynomial perfectly gets the derivative here. So when you put in x is equal to a here, this will be f prime of a. This thing evaluated at a will also be f prime of a, because differentiating this, all of these will still have powers of x minus a, so they'll all go to 0. This is gone, you'll just have this bit. So you've got minus f prime of a, and this bit's still got a power of x minus a, and so it goes to 0 as well. So overall this goes to f prime of a minus f prime of a, which is 0. So the derivative of the difference is 0 as well. So then you can apply Rolle's theorem to the derivative d prime, and you know therefore that there must be some point in between them where its derivative is equal to 0, i.e. the second derivative of our initial difference is equal to 0. So we can then call that our alpha 1, let's say. So this could have been alpha 0. So we've then got alpha 1, which is a point where the second derivative is equal to 0, but we then also know that the second derivative is equal to 0 at x is equal to a, again, because if you differentiate this twice, you'll get f double prime here, and then differentiating the Taylor polynomial, this will have gone, this will have gone, all these higher terms will still have powers of x minus a. This one, though, this will have differentiated completely down to 1, so you'll just have f double prime of a. So when you evaluate this at this thing's second derivative at x is equal to a, it gives you f double prime of a. So just writing a little bit of this out. So the second derivative of the difference is going to be the second derivative of the function minus the second derivative of the Taylor polynomial minus, then we'll have c x minus a to the power of n minus 1 over n minus 1 factorial. So when you stick in x is equal to a here, that goes to 0. All of these other higher terms in the Taylor polynomial have still got x minus a in, so they all go to 0. So it's just this one that gives you something. So you just get f double prime evaluated at a minus f double prime evaluated at a. So again, you get 0. So at a, the second derivative is 0, and at a alpha 1, it's 0. And then you can apply Rolle's theorem again and say there must be a point in between these two, which we could call alpha 2, where the derivative of that function is equal to 0, i.e. the third derivative now is equal to 0, and this continues on. So this continues on right up until the nth derivative, and ideally what I would have done is actually label these alphas up differently, so that their numbers correspond to which derivative they're on. We should have labeled them alpha 1, alpha 2, and alpha 3. So alpha 0 should have been alpha 1, alpha 1 should have been alpha 2, alpha 2 should have been alpha 3. Those are better names for them. It doesn't matter, but it allows us to more easily keep track of what they relate to. So alpha 1 is the point where the first derivative is equal to 0. Alpha 2 is the point where the second derivative is equal to 0. Alpha 3 is the point where the third derivative is equal to 0. So this will continue on right the way up to alpha n and the nth derivative. So we'll find some alpha n in between a and x0 such that the nth derivative is equal to 0 at that point. If we think about what the nth derivative of the difference is, it's going to be the nth derivative of the function. And then if we've differentiated the Taylor polynomial, the nth Taylor polynomial n times, all we'll be left with is fn evaluated at a. So just to demonstrate that, here's the expression for the nth Taylor polynomial. All of these lower terms will have differentiated away to 0, and then this term differentiated n times. The final term will just have differentiated down to 1, this bit. So you'll just have 1 times this, which is the nth derivative of f evaluated at a. And then if we think about what our correction term has become, so differentiating this thing n times, well, this hasn't completely differentiated away, but it has differentiated down to x minus a to the power of 1. The factorial thing is completely differentiated away, so just have minus c times x minus a. So now we apply Rolle's theorem one final time. So this function here, if you evaluate it as x is equal to a, stick in a here, you get these things cancel to 0. This is 0, so it's equal to 0. So at a, the nth derivative is equal to 0. We also have this alpha n where the nth derivative is equal to 0. So between those two, we now apply Rolle's theorem and say there must exist some final point, which is our final xi. So there must exist a xi. And all we can really say about xi is that it's somewhere within the interval a to x0 overall, even though, of course, really it's in the interval from a to alpha n, but we don't know where alpha n is. It could be indefinitely close to x0 because all of these alphas subsequently could have been really, really close to x0. So overall, all we can say about xi is that it's somewhere in this interval. Yes, it's true that it's to the left of all of these alphas that have come before it, but we don't know where they are, so we can't more accurately place this. So there exists some xi in that interval such that the derivative of this thing is equal to 0. So let's do that. The n plus 1th derivative then of x is equal to the n plus 1th derivative of x. Now that thing vanishes, this thing goes to minus c, so minus c. So it exists some psi such that this derivative is equal to 0 therefore. So when you put in xi in here, you should get 0, and therefore we can conclude that c is actually equal to the n plus 1th derivative of the original function evaluated at whatever that magic xi is equal to. So there you go, Taylor's magic theorem comes from applying Rolle's theorem multiple times. So I'll just once again state again what this theorem says, and then we'll look at using it to show that the Taylor expansion for e to the x actually converges. So what the theorem says is that if you have a Taylor expansion centered at x is equal to a, and you're looking at the nth Taylor polynomial, then you can think about how to make a correction term for that nth Taylor polynomial so that it works at some specific point. So you do have to choose a point. So we choose this point x0 here, and you can think, can I add on a correction term that makes my nth Taylor polynomial work perfectly at that point? And you can do that, and what Taylor's theorem tells you is it tells you something very interesting about what this coefficient is equal to that you need here. It tells you that there exists a xi in between the center point and your x0, so in this interval, such that when you evaluate the n plus 1th derivative of the original function at that point, it is equal to the perfect coefficient that you need to make this correction term work. That is what Taylor's theorem says. And that works for whatever x0. And even though we've always had x0 to the right of a, hopefully you can think about that argument that we've just used involving multiple Rolle's theorems. It will work just as validly if x0 is on the left as it did when x0 was on the right. So we're going to now look at the Taylor expansion of e to the x and understand why it converges to e to the x for all of the real line. So we're looking at the function e to the x, and this function is special because of the fact that all of its derivatives are equal to it. So if you differentiate it once, you get e to the x. If you differentiate it twice, you get e to the x. So dn dx to the n of e to the x is equal to e to the x. So we're going to make Taylor polynomials a Taylor expansion that is centered around x is equal to 0, so a Maclaurin series if you like. So a is going to equal 0, and therefore we're going to want the derivatives of e to the x evaluated at x is equal to 0. So all of those derivatives are going to be e to the 0, which is just equal to 1. And that means that our Taylor polynomials, so Pnx, are going to be of the form sum from I is equal to 0 to n of just x to the I over I factorial, because all of those coefficients, all of those derivatives are just equal to 1. And now the question that we are really interested in is understanding why this infinite power series, so sum from I is equal to 0 to infinity of xi to the power of I, not to the power of I, over I factorial, why this converges to e to the x for all x is an element of the real line. That's the question we want to answer. Now, this argument can get very confusing because of the fact that we're going to leave in this general x. I have toyed with the idea of turning it into an x0 so that it looks less confusing. However, I don't actually think that that makes it look less confusing, so I'm not going to do that. I'm going to leave it as the general x. But what you need to understand is that you can imagine now fixing the x. Yes, our argument is going to be valid for all x in the real line, but I want you to stop viewing this as necessarily a function. We're viewing it as an infinite series that, yes, has this variable that can be changed in it, but really what we're concentrating on is that infinite series, and we want to understand why it converges to this. It's just the case that we're doing it for a general case where you can have any x here and the result still holds true and is valid. So what we want to understand then is why, whoops, thought I had the pen, why when we take the limit as n approaches infinity of these sequence of partial sums, so sum from I is equal to 0 to n of xi over I factorial, why this is equal to e to the x. And again, remember, we have fixed x. Imagine we have fixed x. Yes, we haven't said exactly what x is equal to. It's going to be the case that x can be any element of the real line, and this argument holds valid. But now what you need to do is think of x just as a number. Don't think of this as a function. So, this is a great big sequence, and it's somehow converging on this. What we can actually do is something quite clever here. We can rewrite e to the x as the limit as n approaches infinity of e to the x, because e to the x is just a constant. Remember, x is just a number, so this is just a constant. So this sequence is just a sequence of constants over and over again, this e to the x, e to the x, e to the x, e to the x, and of course it converges on e to the x. But this then allows us to combine these two limits together. So we're going to take this one on the left onto the right, and we'll therefore get that the limit as n approaches infinity of e to the x minus this partial sum, so sum from I is equal to 0 to n of x to the I over I factorial, this needs to be equal to 0. So if we can prove that this is the case, that this thing converges to 0, then we're done. We've proven that this thing converges to this. And since we didn't make any assumptions about x could have been a general real number, then we've proven it for the whole real line. Now time to apply Taylor's theorem and time for a picture to justify this. And this is the point where you really could get confused about what this x means. So, well, that's a horrible straight line. So a is equal to 0 is the centre of our Taylor polynomial, and we now have some x that is fixed for our problem. And yes, we're dealing with a general x, but for the basis of this great big infinite series converging, x is fixed. And what we are asking is, what is the difference between e to the x and its nth Taylor polynomial at this point here, where this Taylor polynomial is centered at 0. And what Taylor's theorem tells us is that we could add on a correction term that would make the Taylor polynomial correct at that point x. So if we now, and this is why it's confusing, because we're switching between thinking of this as having a specified x and thinking of it as a function. So really here, these ones that I'm circling in red here, these are the ones that pertain to this specific x, and now I'm about to think in terms of a general function again. So now when I write x, we're going back to thinking about the specific function. So, get rid of that red. So if we think about this Taylor polynomial, sum from I is equal to 0 to n of x to the I over I factorial, this is some function on the real line. And we have seen how we were approximating e to the x with this, and we can make it work at this specific x that is circled in red here by adding on a correction term, so a term of this form, x to the power of n plus 1 over n plus 1 factorial. And we know that that c will be equal to, by Taylor's theorem, the n plus 1th derivative of our function evaluated at some xi that is in between 0 and our x in red here. So, if we now go back to our specific x here, if we want to know what the difference between e to the x and the nth Taylor polynomial evaluated at that specific x is equal to, we can say that it will be equal to this thing, where you plug in your specific x in now, so red x is going in here, and then this coefficient will be the n plus 1th derivative of the function evaluated at some xi here. So what we can now say is that this is the limit as n approaches infinity of the n plus 1th derivative. Now, in our specific case, the n plus 1th derivative is going to be e to the, as a function, it's going to be e to the x. So evaluating this at some xi, it's going to be e to the xi, and then x to the power of n plus 1 over n plus 1 factorial. Where now, again, this is red x, and this is why it's really confusing. So we've flitted between thinking of x as a variable for a function and flitting between x being a specified x over here. So we know that this is right, that if we have this function e to the x and we have this Taylor polynomial which is also a function here, we can make it right at a specific value, like so. If we then stick in that specific value, so if we put in specific value of x, so we put in red x into all of these, then this becomes an equality in that case, and therefore we could take this thing onto this side, so we could have e to the specific x minus this is equal to this, where you have specific x put in here, and that's all we've done here. That's this thing, and we've replaced it by that. That's what we've done here, and I hope I haven't lost you with that, or you don't think that what I've done is dodgy there. It is confusing though. This is why I thought about renaming this x0. It might have been better to do that in hindsight, because of the fact that we've flitted between thinking of x as a variable in a function and thinking of x as a fixed value that we're using in these infinite power series. So this is the genius of this now. We can bound this thing because of the fact that we know something about the exponential function. So drawing on the exponential function here, we know it goes up. It's a monotonically increasing function. It's 1 at x is equal to 0. So for our x value, x red here, the maximum that e to the xi can possibly be equal to is going to actually be e to the red x here. Because for any of these values between 0 and x, e to the xi is going to be less than this. So the maximum thing it can possibly be is equal to this. So if we want to prove this limit goes to 0, what we can actually just prove is that if we replace e to the xi with e to the x, if that thing goes to 0, then this thing most definitely will go to 0, because all of these terms of that sequence would be less than this. So what I'm going to do is say, no, I want the white pen, e to the xi x to the n plus 1 over n plus 1 factorial is always going to be less than e to the x over times x to the n plus 1 over n plus 1 factorial. So if I can prove that this sequence goes to 0, then by the Squeeze theorem I will have proved that this thing goes to 0 as well. So just to go over this again, what we're actually dealing with at the moment, and we are going to have to split it into two cases, is we're dealing with the case that x is a positive value, and we'll look at the case where x is a negative value in just a moment. But for x is a positive value, we are trying to prove that this thing goes to 0. The issue is this. This is going to continually change with n, so if you imagine this as an infinite sequence, as n gets bigger, this is going to continuously change. This xi is going to change. So every different Taylor polynomial that you're putting here will have a different xi that you need. However, what we can do is bound it. We can say whatever that xi is equal to, it's somewhere in between 0 and x, and therefore its value of e to the xi is always going to be less than e of this thing that's bounding it above, the upper bound. So its upper bound is x. So whatever xi is equal to, e to the xi is always going to be less than e to the x. So all of these terms of that sequence are going to be less than these terms. So if we can prove this thing goes to 0, then this thing is forced to go to 0 also. And again, that's using the fact that actually these are all going to be positive if we're dealing with the case where x is greater than 0, because these are all going to be positive in that case. This is always positive and this is positive. So we're trapping it between 0 and something that's then going to 0. So by the Squeeze theorem, this will be forced to 0 as well, is the idea. So then what we can do is just look at that limit then. So limit as n approaches infinity of e to the x, x to the n plus 1 over n plus 1 factorial, and see what that does. Well, don't get afraid by this. E to the x is just a constant as far as the limit is concerned. N is what's changing, so you can pull that out, that e to the x. And then we've just got a limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial. And this limit is going to equal 0. The reason being that eventually this n plus 1 factorial is going to start growing at a bigger rate than x. So remember, x is some constant. So if you think about what these terms are equal to, so let's imagine having the first term. So the first term is going to be x to the power of 2 over 2 factorial. Then the next term is going to be x cubed over 3 factorial. The next term is going to be x to the 4 over 4 factorial. And again, don't get confused by that x. Remember, x is now just a constant. It's that fixed red x. It's some number. Now, if you look at the ratio then between the terms, the ratio here is x divided by 4. The next ratio is going to be x over 5. The next ratio is going to be x over 6. Now, x might be an enormous number, but at some point, the thing on the bottom is going to overtake this, and therefore we will be multiplying by something that is less than 1, and then indefinitely afterwards, or forever afterwards, we will be multiplying by something, again, that is smaller than 1, and is getting progressively smaller, because this thing is just going to get bigger and bigger and bigger and go off to infinity. This thing is a constant. So at some point, if, just as an example, let's say x was equal to 100, well, at some point down the line, this thing at the bottom is going to be 100 billion. So the thing that you're going to be multiplying by is going to be 100 over 100 billion, and then the next one along is going to be multiplying by 100 over 100 billion plus 1, etc. And you're going to multiply by all of them going off to infinity. So you can see that it's going to become vanishingly small. This factorial destroys this on the top. So it totally takes over, and that is going to converge to 0. So indeed, this limit is equal to 0. So let's just go over what we've done there again, and then we'll go over the case where x is less than 0. So back up to here. So we were taking initially the example that we're dealing with an x that is greater than 0, and we want to see why this thing is going to converge to this, and we're thinking of x as now this constant that is greater than 0. So we've then said, if this converges to this, then this difference between them, the e of x minus this thing should be converging to 0. That's all perfectly fine. This is the confusing bit where we have now said we can use Taylor's theorem to get a grip on how big this error in between them is going to be. So we know that for this given x, we can put a correction polynomial in that will make this Taylor polynomial right at that point. And we also know that the coefficient that is needed in front of this error polynomial is going to be the n plus 1th derivative of the initial function evaluated at some xi that is in between 0 and x. So what we can now do is say that this minus this evaluated at this specific x is equal to this thing. And that's exactly what we've done. We've replaced it with this. So we've now got a sequence of terms that looks like this. Now the problem with that is that these xi's are not fixed. They will change for every single one of the terms of that sequence. So as you go to a higher n, the correction xi that you're going to need there is going to change. Now thankfully the function e to the x is very simple, so at least the derivative doesn't change. For more complicated function, the actual thing that you'll have here will change, but because e to the x, its derivative is always equal to e to the x, at the very least the derivative doesn't change, but the point that you're having to put in is going to be moving around. However, what I've said is that we can bound this because xi is always going to be between 0 and x, so the maximum e to the xi could possibly be is going to be this value at our e to the x. We also know that all of these are going to be positive because x is greater than 0, so we've now bounded it in between these two things. So if we can prove that this thing goes to 0, then we'll have proven that these things also have to go to 0, because whatever these xi's are in each of the terms of this sequence, this thing is always going to overall be less than this thing. And then we've done that argument that this thing does indeed go to 0. So therefore this thing goes to 0, and therefore this overall goes to 0. Now for the example that x is a negative number now, so this time x is over here, you can, and this is red x, you can apply Taylor's theorem exactly the same. So it's true that there will be some xi in here such that that difference, or this difference here, is equal to something of this form here. And depending on what your n is, your xi will change. And therefore, again, we just need to prove that this limit is going to be 0. Now, the thing that's slightly different here is we can't immediately conclude that all of the terms are greater than 0 because x is now less than 0, and for the odd powers is going to be negative. So instead what we can look at is thinking about the absolute value of this term, of these terms of the sequence instead. So e to the xi x to the n plus 1 over n plus 1 factorial. And now if we can prove that that sequence of absolute values, so all positive things, is going to go to 0, then we will have also shown that the overall sequence goes to 0. Because if you think about it, so if you imagine, if you have sequences that are flitting between positive and negative, like so, if overall the size of the terms of the sequence is going to 0, getting smaller and smaller and smaller, then they are converging in on 0. They might be converging in from either side, so all the positive ones are converging in from this side and all the negative ones are converging in from this side, but overall the thing is converging on 0. So that's a special thing about sequences where the limit is equal to 0, that if the limit of the absolute value of the sequence is equal to 0, you can conclude that the limit of the overall sequence is equal to 0. So what we can instead look at is this sequence of absolute values. Now, the exponential function is always positive, so its absolute value is just itself. The factorial is always positive, so its absolute value is just itself. And then x to the power of n plus 1 is just going to be mod of x to the power of n plus 1. So that's what this sequence actually becomes. And now we know all of these terms are going to be greater than or equal to 0. So if we can bound it above by another sequence that is then converging to 0, we can then apply the Squeeze theorem to say that it's converging to 0, and then use what we've just discussed to say that this converges to 0. So again, we have this problem that these xi's are changing for each term of the sequence. Thankfully, the derivative at least isn't changing, but the xi's are going to be changing. So we need to bound them again by something. And this time we don't want to bound them by e to the x, because e to the x is actually going to be smaller than e to the xi, because we're dealing with the negative side. So e to the x is obviously smaller than e to the xi. So instead we want to bound it by this thing above, the other boundary, which is e to the 0, which is equal to 1. So it's even more beautiful. We can just replace, in this case, e to the xi with 1. So it's going to be less than or equal to mod of x to the power of n plus 1 over n plus 1 factorial. And again, x is just some constant, some negative number now, whereas n plus 1 factorial is going off to infinity. So this thing is going to dwarf this thing, it's going to destroy it, and this indeed is going to go to 0 for exactly the same arguments as we've had before. So we can therefore conclude this goes to 0, and therefore conclude that this goes to 0. So overall what we have done there is we have used Taylor's theorem to show that for a general red x here, this limit is indeed equal to 0. So truly, this limit is equal to e to the x. So now what we can do is say, as we've proven this for a general x, it therefore holds for all x is an element of the real line. So we have shown what we wanted to show, that this famous power series becomes this, as you take it off to infinity. So I hope you've managed to follow that. Thank you for watching the video.